And now it's my honor to introduce Professor Saulius Juodkazis from Swinburne University at Australia. So he graduated from Vilnius University and got PhD from Lyon University and Vilnius University. And in 1998, he moved to Japan, to Hokkaido, Tokushima universities, and made a number of works for micro-fabrication. And then he became a professor at Swinburne and head of Nanofabrication laboratory, and numerous work dedicated to photonic crystals, optical memory, and so on. Plasmonic interaction has made him one of the leading persons in this field. So with 11,000 citations, he is one of the leading groups in the worldwide. So it's my pleasure to welcome you here, and Saulius, your word now.
Yeah. Thank you very much for introduction. It's always good to be here. It's the largest conference in Lithuania, as I was told, so it's great, and good to be back in Vilnius. So today, immediately jump to presentation. I have 30 slides and 45 minutes. So, and this is new material, and the second part is not published, so it's open readings. That's why. So we have some challenges in 3D nanofabrication, especially when we reaching the scales of single nanometers. Yeah, we know laser fabrication is great, and we can reach those tens of nanometer resolution, but it's always challenged. So we have more mature technologies. For example, we have electron beam milling techniques, and we have also electron beam lithography, which can really deliver nanoscale resolution. But they are charged particles, and they are causing some problems. And we were somehow exploring, can light help to make those charging problems during fabrication disappear? And this is very, very, very valid question, because when you, for example, in this geometry, when you have gallium ions milling your nanostructures and you are observing them by electrons, you don't know which is fooling you if you see some strange shapes. So it's milling, which is not correct, or it's electron imaging. So how to solve the problem? It will be first part, and the second part is about optical characterization. Once we fabricate nanostructures, usually we're interested in some strange shapes. They obviously sub-wavelengths, and we are characterizing them optically in infrared and visible wavelengths. So optical characterization for this talk is measuring of absorption and measuring of birefringence. So how to, can we extract more information than the just average when we measure nanoscale features in our images? So nanotechnology is really a 3D challenge. If you see the range which we should reach in single nanometer wavelengths, so it's some of our chips which we are fabricating should interface with bio-objects which are on that scale. Nothing is flat on 1 nanometer scale. And we know from the transistor development, so this is most mature technology, and once we begin to go to the resolutions which are in around 20 nanometers, our field transistors begin to be three-dimensional, not flat anymore. And this was the place where all that roadmap was slowing down. So for me, this is the challenge, which is three-dimensional structures, which probably we can tackle if we are using three-dimensional approach in our fabrication. And one of the kind of emerging ways of fabricating materials on 3D with 3D capability by direct writing, so it's slow, but actually deliver the final device what you want. So this is available from Ramo, this group in Italy. It's already Cleanroom is providing commercial service. You can make IFM tips more sharp. And this is just direct milling using gallium ions. And these tips are really working very nice in the labs. So this approach of milling directly with ions is actually very powerful. But for that, you need to have ions which are focused very, very well. So the ion beam which we have in our lab is having the cross-section of the of the beam around 10 nanometers. And this is intensity distribution of the beam, and this is logarithmic scale, so we have actually cross-section here. But what is important that those wings, they're actually very low in intensity, because other points on this map are from other commercial devices, other FAB systems. We can't disclose their names, but if you're using those kind of profiles, you will never reach the resolutions which is shown here, because once you mill one path in your structure, when you crisscross, you will open much wider grooves. And the reason is that once you hit your sample edge at a very high angle, the milling rate can be 10 times higher. So you always want to mill just at the tip of your intensity profile of ion beam. So once you have good focused gallium ion beam, you can do inscriptions in your nanoparticles. This was with the flavor of surface enhanced Raman scattering using chiral gold particles. And it's really full control. You inscribe the structures with a high fidelity, and you can reach aspect ratio is 10, so it's just spotted gold, and you can open the gaps which are in tens of nanometers. All this is good. Just let's jump to another application where actually electrons can help to reach nanoscale resolution when you are using focused ion beam. And this was a French student project. They came to our lab and they were exploring what the smallest hole you can open in the membrane of silicon nitride. And this is interesting for translocation of DNA, for example. So we know that our gallium ion beams has 10 nanometer resolution, so can we open something smaller? And never worked out that we can make really nanoscale holes. So usually, very quickly you make something much larger, which is 100 nanometers here or so. And then you obviously want to know what is the size, and the students were imaging this with the electron beam. And what you actually recognize that by imaging with scanning electrons, you're actually closing the hole which you milled at the beginning. So, and this is the plot. So you see that you can open a hole which is in tens or 100 or 200 nanometers, but then you can close to this range, which is really in single digits of nanometers. So we don't have resolution which we require, but actually we can use remelting and surface tension effects introduced by gentle electron scanning during SEM, and we are closing the gap. Okay, so where there is challenge is when you want to make this fast. So here is just last example of this nano editing. For example, you mill groove, and then you just scan electron beam in the places you want. So you actually stitch your hole, which was opened in nanomembrane. And if you think, this is already kind of three-dimensional structure because the thickness of membrane is around 20, 30 nanometers. You're opening the similar hole, and then you can stitch it to reach similar resolutions. And if you go to the fast milling, you need to use much higher ion currents. And then what happens that usually you are charging surface. So this is an example how the problem is you can visualize. You have your design. You want to write the circle. You started somewhere, but as you write, your stage is actually moving all okay, but the surface is charging, so you are not focusing ions anymore in the place you want. So your final design is lost, and especially when you mill fast. You need to mill fast if you want to create fields of particles, fields of devices. They should be identical, same geometry, and you should make it fast. So it's somehow, it's not working what I showed. Resolution is good. You can reach really full control on nanoscale. But when you go to the faster production of larger areas, it's a problem. How we tackle the problem? We used UV LED diode. We put it in a way that we can illuminate our sample. And we chose, in this case, it was titania, so it's dielectric, and even we placed on capped on tape, which is really dielectric, so we're making charging even more problematic. You can't release charge from the surface, because usually if you do some imaging or FAB, you place carbon tape, which is reducing your charges from the irradiated area by ions or electrons. Okay, so we created more tricky situation for ourselves, and then we shine UV light from our LED, and we are carrying out milling. We start here, we go full circle, and we reach the place we want. And this happens only when we have really very short wavelength UV light. So it's that UV light is actually making freeing electrons from the titania substrate. So what happens here, it's our kind of understanding, which is can be debated in more details. When you mill, you certainly deposit positive charge, but you create a lot of secondary electrons because you are damaging your material. And those electrons are very, very localized, so they are preventing focusing of your ions perfectly. So when you shine UV light, you're actually homogenizing the charge on the surface. Probably the surface is still charged, but it's not anymore inhomogeneous, and then you can mill as you want. So the work function to free electrons from titania is when you reach the wavelengths of work function, actually then you can fabricate very nicely your structure. So if you change your LED illumination wavelengths, the longer wavelengths you go, you are losing precision. When you mill, in this case, it was really high current, fast milling. We create defects as we cut the material. So we create some traps for electrons. And those traps can be, electrons can be released from those traps even at slightly longer wavelengths than from Fermi level, which is work function. That's why it's still, there is some effect for longer wavelengths, but the best wavelengths is really when it is very short. Well, when you image by electron beam, what we are doing with FAB, it also can trick you. And here, we already took the structure fabricated before by liftoff. We have cross, which is gold, and sitting on the substrate, which we know that it's charging. So if there is no any illumination of UV LED, so we see that shape is somehow not reproduced. We know that it should be really cross. When we illuminate deep UV, so we recognize the shape we want and believe that we fabricated. Here it's another example. We have gold sitting on silicon. So silicon is semiconductor, and it's just to show that it's still charging. If you have no LED illumination, you have drift of the edge and changing of the geometry during the imaging. And if you switch on your UV light, so then you have decent edge as you fabricate. So this is kind of summary. And bringing one more important aspect, that if you illuminate UV light, you have another way of recognizing your materials. So here we place different metals on the surface, and their work functions are different. So the most white one is gold, because it's charging. So to free electrons from gold, you need shorter wavelengths. And from aluminum, you can do it with a longer wavelengths. And we see it's as less charging. It's more black in this image. This image can be slightly different, depends how you register them with the electrons which are just bouncing back into the beam, or if your detector is at very large angle for secondary electrons. But what I want to show here that we bring a new way of contrast to SEM. Okay, so then its second part, which is new. This is optical characterization of when you reach sub-wavelengths. What we want to know, and is it possible to get some extra information from the measurement of absorbance and birefringence. So we define material as basically refractive index, real and imaginary part. So we know these parameters, we know how it will interact with light. When we go to smaller scale, we fabricate smaller features on our samples, and we are characterizing them with imaging, then we begin somehow to be sensitive to smaller, to change of n and change of k. So this is birefringence and dichroism, and they are showing anisotropy of optical properties of materials, and usually they are just by definition direction dependent. And we know this from birefringence. So this is the wave plate commercialized by Altechna, and so what they are doing is creating nanogratings using Pharos laser, which is made not close from here, not far from here. And those nanogratings, they are patterned in a specific way that the birefringence, which is introduced, makes certain phase delay, and this is used for polarization optical applications to change polarization or to generate optical vortices. So what you see here is basically the color visualized birefringence map. But the structure which is recorded there is actually control of birefringence on nanoscale, sub-wavelength scale for visible imaging. So this image is taken in invisible around the wave plate, which gives colors is green color. So somehow we know that what I just told, this is really what we are using. The image here is an optical domain, and somehow we are using those elements for delta n effect, but actually we're always interested how much losses we have. And the question is how to measure and determine them independently. And the problem actually comes, as I will show in the next slides, that what we are measuring always transmission. And if we go into absorbance, we're still kind of just calculating something out of transmission. And if we want now to determine independently birefringence and dichroism by measuring one entity, which is transmittance, how to do that? So here it's another example. We are more interested in infrared absorbance. So we go to that so-called fingerprinting region for polymers. In this case, so some polymer which is making some fancy spherulite crystals, which we can visualize with the optical wavelength. So it's very, very short wavelengths. We see that structure is very complex. But for characterization for, let's say, sensor field, you usually go for this wavelength range, which is 3 to 10 microns. So this is the fingerprinting region, because you can pinpoint some transitions which we know. So you can actually recognize material when you are looking in the spectral range. But here, somehow we are almost not interested at all in refractive index properties. We're always interested only in the absorbance. And if you look at those transitions, for example, for this particular material, you can recognize the bands, and they are perpendicular, for example. Let's remember this. But they are sitting on the backbone of polymer. And in optical domain, backbone of polymer or stretched polymer, it would be definition of optical axis, fast or slow. And it is exactly, it is this way because we know this from optical domain. But somehow, for infrared community, they're not really interested in what is happening with the refractive index. Thinking about optical domain, visible domain, you think that, okay, if I measure some absorbance at the transition place, probably I should be out of resonance when I'm measuring some birefringent response. So this can be done, but somehow it is ignored, probably for good reason if it is not very important. But I think I will show that it's actually important. So using another very important feature in infrared spectroscopy, that each point of your image has the spectral information. So for example, you measure once your image, and you can simply look for certain wavelengths, and you recall the absorbance at this particular wavelength. And these two peaks actually from this plot here, and they are perpendicular. If you do some simple algebra, you can recognize the orientation of those bands, and you see that this is perpendicular to that just by this color image. So somehow, with the hyperspectral imaging, in each point, I have all spectrum measured of my object, and also I can calculate the orientation. But in this case, orientation is simply how the absorbing dipoles are oriented, and I am blind to response which is due to refractive index effects. So let's look how we are measuring retardance, for example. So usually the formula is here for transmittance. You have polarizer, you have your sample, and you have analyzer. All this formula is right when you have no reflection and you have no absorbance. And this is the visualization of this, this formula. So if you take your sample out and you shine light and linearly polarized and you rotate, you will see a transmittant pattern like this. If you don't, and if you place inside the birefringent object with the slow and fast axis and you rotate it, you will get this image. Let's remember this. We will come back to this. So this is a recipe how we measure birefringence. So we know thickness, we know wavelengths. From transmittance, we actually can recover birefringence. But somehow here we are blind to absorbance. So when we measure absorbance, what we do is, again, we just look for transmission. We use polarized light. We detect it. And as absorbing dipole is aligned to the field, it will be maximum absorption, as we know, and it will repeat after 180 degrees. This is taken here with this cosinus here. So we know how absorbance should behave if we are rotating sample or rotating linearly polarized light. So this is how we measure absorbance. Again, in this formula, we are blind to birefringence. The colleagues in Tokyo Institute of Technology, Morikawa Sensei group, they introduced some years ago elegant way of measuring orientation of dipoles in your absorbing sample. So it's the same measurement. So you have linearly polarized light, and you measure it at 4 different angles, which are different by 45 degrees. And then just by simple calculation, you will find what is the orientation of your absorbing dipoles. And actually, those 4 angles can be arbitrary. You don't know your orientation of absorbers in your sample, or you don't care about your linearly polarized orientation of your light. You measure 4 points, you calculate, you will have orientation of dipole. So I here just show it. It's actually coincides with the 1 point, but it's not necessary. So 4-point measurements usually can be noisy. So if you have time and you can measure more orientations, you do that, and then you can simply fit your simple function, and you will retrieve the orientation angle of your dipoles. So still, I'm kind of nagging to the same question. Should we somehow know and separate absorbance from birefringence in our measurement? So let's remember the formula I showed before. So this formula is great. We have cross-polarized imaging. It means we are looking usually, if our sample is not birefringent, it's totally dark. So if something is totally dark and you have, in addition, absorption, it's not helping you to detect it. So what to do? So let's rotate our analyzer and make it aligned with the polarizer. So what happens now? So we have light which actually can pass through. But in terms of information, which I'm losing information or not, the question is, when I do this transformation here of angle of my analyzer in this case. In fact, it's not, because what I measure now, it will be the same expression here, but it's only 1 minus, because I aligned this analyzer and polarizer together. So what happens with my image, it just rotates 45 degrees. So each time, my birefringent sample, which has slow and fast axis, if it will be aligned or perpendicular to my analyzer and polarizer, which are now parallel, I will get the minimum. So I will have dark field. So somehow, these 2 formulas are identical in terms of information I can extract. It means that now I can extract the same birefringence, but now my system is transparent. So I have light coming through, and this is important if I'm measuring absorbance, and I want to have signal which is can be measured with a decent signal-to-noise ratio. So we have 2 formulas now, side by side, and this is the same transmittance in a way, because this is transmittance how we measure it through the aligned analyzer and polarizer, and then this is just logarithm of that transmittance, and we have expression for absorption. And then this is also set up, which is nicely working with this formula, because what is important in absorbance simply orientation of the dipole in my sample, and somehow this second analyzer is irrelevant because light just goes through. So all the minimum I will have in transmission from birefringent effects actually will depend on the angular dependence will be 2 theta, and I know this because if we compare these two formulas here, this is cosinus of some angle 2 theta, and this is sinus of 2 theta, but it's square. So this is actually double frequency. So I expect that effects which are linked to birefringence will be spinning twice faster than angle, and if I look for absorbance, it just should repeat as dipole is aligned to electrical field. So this is kind of recipe and a hypothesis to test. So what kind of material we choose for our experiment? Let's do something useful. So let's take paracetamol. We're using it. But all tablets are made from the form 1, which is very easy to produce, as you can buy in drugstore. But in fact, for our body would be something better, which is water soluble, because this is not exactly. So the form 2, which is shown here, an optical image, is much better. It's water soluble, but we don't know how to make stable packaging of that form. So people are interested what kind of structures, what is the domain, how it is melting. All those things are very relevant to pharmacy. So we have our sample. So it's complex. It has some alignments. So let's apply our formulas, which we believe should work. And experiments were carried out in a synchrotron in Melbourne. So it shines very tricky polarization field. So what we did, we simply put the Y grid. And we are following the rule we just discussed before, that analyzer and polarizer should be aligned. We place our sample and we detect entire signal. Let's forget about mapping and pinpointing the pixels. It will be later. So now we're just measuring the transmittance. So this is results, which are points in those plots. We are taking different wave numbers, so different wavelengths, because it's hyperspectral. So in one spectrum, I have all the information. And now let's look for the formula which actually can take care of this double frequency dependence. So this part here will be because of retardants. So I have cosinus 2. And here will be just exponent, which is kind of intensity is decaying. So we expect this. So this is taking care of absorbance part. And from this expressions, we can trace it to the formulas discussed before a few slides ago. So what we see here, let's say, look at this. We have experimental data, and we need to fit it, and to separate effects which are due to birefringence and effects which are due to dichroism. Okay, so we know the rules. So this is the formulas to use. So here, this part is taking care of absorbance, and it's actually one wave. And then this has two waves. It's taking care of retardants. And if I take black and red, I will get the blue. And I can get very decent fit. And then my question before, I was asking why people are not interested in retardance effects when they are looking in very long wavelengths in infrared. Actually, probably they are missing something, because this is not negligible contribution to that signal. So I have birefringent effects kind of hiding in the absorbance if I don't know and don't separate them. Okay, so this is the same story, only for another wavelengths. So it looks like it's working, but now it's for entire integrated spectrum. What we want to do next, we want to go into imaging. So let's remember our good resolution optical image. So we have luxury of good resolution here. And then let's go into something which is almost 10 times longer wavelengths. We don't have great resolution there, but we want to recognize this place. So let's select, in this case was 4 pixels, because 1 pixel is quite noisy. And what you do, you just rotate your sample between two analyzer and polarizer aligned. So you have this messy data here for different angles. And then we select some peak, which is a specific absorbance peak. So it's some specific vibrational transition. And now if I will plot the angular dependence, and I'm fitting this very easily with the single angle dependence. Then if I go to something which is out of resonance, so somewhere it's almost flat, then at some angles actually it's coming up, but it's not really the peak of absorption. If I will take this wave number, and then I plot my data, intensity at that angle, I actually much better fitting this with the 2 theta. So as expected, because here it's probably I'm just sitting somewhere on the polymer chain and it's absorbing. It's my slow axis. And here I have really some absorber which is taking light out of transmission. So we can do imaging. So we know the rule. Let's say we're interested where there is an H vibration. So we calculate from the fit the amplitude of the fit. We can work out the orientation because orientation will be hiding in all those formulas. It was theta minus something. So this is the original orientation, initial orientation of your dipole or slow axis. And then this picture is actually a combination of average absorbance, which is color. From this picture, we can take amplitude, which is length of this rod. And from this picture, we'll take orientation. So kind of putting things together in one place, not to be more complex, but just to show that from single pixel, now we can retrieve more data. OK, so I want to know where there is water sitting in my sample. So I go to this vibrational wave number. And so this is the picture. So no water. This is more rich, or it's probably more thick. So it's also you need to know what you are measuring. And so on. So you go to another band in that material, and you recognize, somehow you recognize the picture which you have luxury invisible domain. And here, we're measuring really at much longer wavelengths. So this was absorbance, but now we are also not blind to a refractive index effect, to birefringency. So if we look for the retardants, which we took just average for all the angles, so this is retardants. So this is the in nanometers. So if you translate for wavelengths, which is in microns, probably it's not a big deal, but still it's something measurable. So we have good sensitivity. So this is optical image. This is the our retardants. So the formula we kind of applied is here. So these angles, actually it's also important to mention that this initial orientation angle, this angle will be the dipole, and this will be the slow axis. So there are these angles plotted for single pixel here, and these are amplitudes of those coefficients here. So this is the data. It's probably less representative, but then what we can do, we can plot them together. Now the length of the line is normalized simply to appreciate the orientation change. So we look for the water, and we have optical domain overlaid with the infrared spectrum. This is our single pixel measurement on the camera. And we can have, from single pixel, we have absorption information. We know how the dipoles are oriented at that particular pixel, and then what is slow axis at that point. OK, so what next? After this, we had the last beamline in synchrotron last year. And they installed first time some focal plane array. So it means before it was really tedious work measuring point by point. FTI is really good because you need simply detector for any intensity. You don't, and mapping you actually should do by scanning your detector. Certainly, if you place the camera, which has many pixels, it's a big advantage. So what we have here, we milled some kind of reference sample, 200 nanometer period of grating, gold sitting on very, very thin sapphire. We made 30 microns. You can't make it thinner. simply not to have any birefringence coming from sapphire. So you measure this 4-angle recipe, so you have 4 angles. You can actually recognize the nice features, or the dipolic nature, which you expect from the grating if you are shining light through. And we know what we milled. So here the wavelength is around 3 microns. Diffraction limit for the optics used was around 5 microns. The pixel size was around wavelength. So we are really going into the wavelength scale measurement, which is tricky. But let's remember, so those are very big numbers, and we are trying to recognize something which has structure of 200 nanometers. So we do the same algebra which I showed before. So we can play with the presentation. If you look for amplitude, you have this picture. You somehow see that center is, and this is basically polarization plot. So all is mixed in the center. Then there is more amplitude coming through at the larger radius, where the curvature of lines is less strong. So if you go for presentation of azimuth, you have recognizing very nice radial structure, as it should be. So then this is combined image absorbance, which is average, together with the lines. The length comes from this plot, and the orientation comes from this. So somehow we are fighting with referees right now. So they are saying you are claiming resolution. No, we're not claiming resolution. We can't beat nature. So if our wavelength is 3 microns, we can't see and resolve features which are 200 nanometers. But actually, because we know what is there, we actually recognize the pattern. So the message here is that just by measuring transmission, decoupling effects which are related to birefringence from effects which are related to dichroism, we actually know a little bit more about our sample. We know that there is some orientation in our sample. So you have the secular features shown here, and then you know that you actually should have them. Okay, I'm perfect on time. I can spend a little bit more time here. The first part, the UV light, it was interesting experiments for a couple of years. What we haven't shown, the really high resolution. So these are features which are large. We recognize the contrast by work function. What is next, missing in this line of work, would be really to show that we have a single nanometer resolution when we apply for electrons, illumination, UV light, and free electrons from our sample. And for me, the biggest beauty would be that if this will work, you will forget buying spin coater for your SEM images, samples when you do SEM imaging, because you just coat by light. And it's, just put a UV lamp in a very dark chamber of your microscope, and actually it will work and do this trick. But probably something is even more important, because in many cases, if you have a field transistor, and you need to know your geometries of your electrodes. So if you have a ring resonator for telecom wavelengths with the nano gaps for the control coupling, and you need to know the structure and geometry. Once you coat with metal, you are losing geometry. Actually, your method is destructive. You can't measure the same device afterwards. So by using UV light, you are welcome to check your morphology and structure of your sample, and then you can still use it if it is electronic transistor or if it is your photonic chip. But this is still to show that it works this way. And second part, I'm ready for challenges and questions, because this is I'm presenting first time, and this is not published. And I think it works. So we did this for paracetamol because it's important material, but probably there are more interesting things to look with this technique. And just as a summary, so what we have now, in single measurement on your FTR microscope, if you just not laser and measure 4 points, you can extract extra information, and you can have your alignment alignment of absorbing species, your dipoles, and actually you can see your slow optical axis orientation at the same pixel. The people in the synchrotron community, there are many questions and still like questions not answered in physics, how phase transitions are happening because it's something spontaneously changing. So how to have theory which is actually describing this, it's still missing. So we need to measure more parameters during the phase transitions. And knowing the orientation is actually one of the parameters of the order. If we go from order to disorder, or if we are growing crystal, this is actually a very key measurement. And with synchrotron, with the very high brightness of the infrared beams, we probably can see what is happening when we are going through the phase transition. So this is interest from the community which is working on synchrotrons. But somehow, this is accessible to any tabletop FTIR microscope we have. We simply need to analyze our data. Okay, so the people behind the results, both Gediminas and Armandas, they did a lot of work with FAB. During their PhD with them, we placed our UV LED into the chamber of scanning electron microscopy without knowledge of our university managers because it would be not allowed. And then 2 visiting students from France, Clemence and Adrien, they're here. So they were stitching those membranes and closing nano holes. And the last team in synchrotron measurements, it was Sunghok, Raghu, and the visitors from Professor Morikawa group from Tokyo Tech. So they are people behind this 4-angle measurement. And somehow I think it's not really appreciated by community that how powerful it could be. You can extract more information from your data. And yes, so thank you for your attention. And this is our funding, not necessary for this work, but this is something we are enjoying over the years. And I should also mention Altechna and Workshop of Photonics here. Okay, so on this I'm closing this talk.
Thank you, Saulius. Thank you. The talk is open for discussions, questions, comments. Yeah?
Thank you for this very nice talk. Could you please a little bit explain when you show the map of the orientation of the axis, and when there is that round object, what was the what's the orientation like? Not in the object, but on the sides, like
here. So this is gold, which is very thick gold. It's I think 200 or 100. No. Okay, it's 100 nanometer pitch. I think the gold thickness was more than 100. It's really blind. It's blocked for light. So it's gold milled through till the sapphire substrate. So it's basically grating you can see through. And then you shine on this grating, you shine very long wavelengths, which is 3 microns. And then you're analyzing your transmitted light. And you're looking for orientation of the dipoles which are absorbing, or in this case, scattering your light back, so not allowing it to get through. So somehow this orientation is simply, if you have wire grid, which will be lines, so it will be linear structure. And then you recover it here, and just to appreciate that this is really deep sub-wavelengths.
May I have one more shot? Why can't you use just a shorter wavelength in this case?
Oh, yeah, it's a good question. So then you go to optics and you can resolve. But what we want to say here that by when you do infrared characterization of your materials, you usually recognize some patterns. And then sometimes you say, oh, this is orientation of my absorbing dipole. But that orientation can be actually affected because that absorbing dipole also can work as a little bit birefringent material at those infrared wavelengths, and people are not really taking care of this effect. So it's not telling the whole picture. I think if the question is about resolution, yes, you just go for the wavelengths when you can resolve it. But what I want to say here that we don't resolve it, but we know that there is something with orientation in that object. And this is, and when you know your sample, so you can begin to expect this is alignment of my, it's probably my crystal is growing this way, and you begin to have a little bit more extra information.
More questions, yeah?
This is just one remark and maybe one question. So the remark would be, am I correct to infer that when you have your 64 by 64 focal plane array, your method is going to become trickier because there's only one center of rotation when you have to rotate your sample. So one pixel is staying in place and the others are running around. That's
yeah, absolutely correct. Yeah.
Okay, so that's just a remark. And the other question is purely by the analogy. You were focused on birefringence, which is sort of akin to linear dichroism in optical spectroscopy. I was wondering if you were to use, for example, left, right hand polarized circular light, would that bring even more interesting information, and maybe not even for the crystalline samples?
Yeah, it's actually good point. And let's remember, we are working with synchrotrons, and for synchrotrons, we don't have that luxury of the polarization optics. So if you need wave plate to make circular polarized light, we still have missing of that technique. So it would be really interesting to see to the effects of the polarization, and obviously also to orbital part of polarization, because all the secondary structures of proteins, they are actually talking to a structure which is actually spiraling. So if we have spin and orbit control in our optics for this exotic, I mean, it's exotic wavelengths for synchrotron, this would be very interesting. And we had the joint work with the Mangirdas group and Avaldas. They actually 3D printed some structures to make some polarization optics for very long wavelengths, for terahertz. So somehow to bring the optics toolbox to those wavelengths would be very interesting. And you are very right that working with spin and probably adding orbit would be more information can be extracted about circular dichroism.
Yeah. More questions, comments? So my question would be very simple. What's the signal-to-noise ratio in your signal, and how quick is the experiment? Because you have making pixel-to-pixel imaging.
Oh yeah, good question. So I think the most raw data from experiment is this. Yeah, so this was actually pixel by pixel scanning. It was tedious work. When you go to synchrotron, it's 3 days and 3 nights non-stop. So one image like that is scanned probably over the 4 or 5 hours.
Okay.
So it's really long, and yeah, then you, just by measuring, you kind of, this we call good results. So it's signal to noise not that bad. But yeah, it's you need better signals. You work longer. That's why the focal point array argument is very, very strong, because then you immediately change by 3 orders of magnitude your acquisition. But it's very right. So you can't rotate sample. You need to know what you are doing.
You can find that back. You just need to
yeah, you recalculate.
Rearrange it. It's going to be more work.
More questions, comments? If not, thanks again for a nice talk.
Thank you.